is Unit 5, Lesson 8. We're going to talk about complex numbers and powers of I. We're going to start with powers of I because I think that would be a good thing to start with. We just learned that the square root of -1 is I. And so if we take that and we have I squared, we know that I squared is I times I, which means that would be the square root of -1 times the square root of -1. And we learned that anytime we have two square roots multiplied by each other, those roots will cancel each other out, kind of like square root of 5 times square root of 5 is 5. That would be equal to -1. So I squared is equal to -1. They are the same thing. So anytime we have I to the second power, we can replace that with a -1. So if we have something like this, where we've got I to the power of 60, well, we need to understand that anytime we have an even powered I, then we can cancel things out using that I squared, understanding that it is a -1. So if we can express our power of I as a power of I squared, then it's going to make this a lot easier to solve. So what I'm going to do is I'm going to break down this I to the 60th power to something that's easier to work with. So I know that I squared will cancel out. I know that I squared is -1. So I'm going to replace I to the 60th power with I squared to some power that would be equivalent to 60. Well, if you think about that, what power could I put out here that would make this a 60? Hopefully you're saying the power of 30. I squared to the power of 30 would be I to the 60th. So we've just changed what that thing looks like. We didn't change its value, we just made it look different, kind of like what we do with fractions sometimes. So now I know that I squared is -1. So I can replace I squared with a -1. And now I have -1 to the 30th power. Well, hopefully you understand that it doesn't matter how many times I write -1. If we have an even number of those -1s, every other one is going to cancel out to a 1, because if you think about it, -1 times -1 is 1. If I do that again, -1 times -1 is 1. So for every two -1s that I have, we're going to have a 1. So that means if we have a -1 to an even power, all the negatives are going to cancel out and just leave us with 1. So I to the 60 is 1 when it's simplified. If you look at this next one, it's an odd power, I to the 45th power. With I to the 45th power, we're going to do something similar, but we need to recognize that this power of I is odd. It's not even. So I can cancel out I squareds because those are even powers, but if I have an odd power, I'm going to have to recognize that I to the 45th is the same thing as I times I to the 44th power. If you think about it, when our bases are the same, we can add the exponents to get our final power. We're just breaking it down further. So we know that I to the 1st times I to the 44th is I to the 45th. And then with this I to the 44, we can do something similar to what we did here with I to the 60. This odd I is going to keep coming down. This one I can write as a power of I squared. Well, that would be I squared to the what power? To make it 44, we would need a 22, I squared to the 22nd power. So then we have an I times I squared is -1, and -1 to an even power would just be 1. So that's I times 1, or I. In the next one, this is I to the 35th power. Again, it's an odd power. So I'm going to take that odd I out. That's I times I to the 34th power, because our 1 plus 34 is 35. I'm going to rewrite the I to the 34th power as I squared to the 17th power, because 2 times 17 will give me the 34. And then I know that this I is going to just come down. I squared is -1. A negative number to an odd power is going to be a negative. And no matter how many times we multiply 1 times itself, we're going to get 1. So negative 1 to the 17th power is negative 1. So we have I times negative 1, which is negative I. For the next one, I to the 16th, well, that's an even power. So that's I squared to the 8th. I squared is negative 1. So negative 1 to the 8th will be a positive 1. The negative to an even power is a positive. So notice here, no matter what we do, our answers, and I don't have the other answer that we could have is a negative 1. So we're either going to get 1, negative 1, I, or negative I for every single power of I, as long as we follow this pattern. The next one is I to the 58th. See if you can get that. Pause the video, see if you can do I to the 58th on your own. Okay, so looking at this one, I to the 58th, 58 is an even number, so that's the same as having I squared to the 29th power. I squared, 2 times 29 is 58. So if we do that, I squared is negative 1, and negative 1 to an odd power, a negative number to an odd power will be a negative, and it's going to be negative 1. So notice, no matter what we did, all of our powers of I ended up either being I, negative I, 1, or negative 1. And that's always going to be the case. So what will we do if we have powers of I multiplied together? Well, in this, we can keep the base, I, and add the exponents together. 12 plus 4 is 16. 16 plus 6 is 22. So we have I to the 22nd. And then your math from here on out is the same. We would have an I squared to the 11th. I squared is negative 1. Negative 1 to an odd power is a negative 1. So very similar, we just had to multiply them together first. Remember, when we multiply monomials, we have to add the exponents. You keep the base and add the exponents. Here we have complex numbers. We're going to do some operations on complex numbers. A complex number is in the form a plus or minus bi. The a will be the real part. The bi will be the imaginary part. It has an I attached to the number. So basically what we have here is we have a complex number plus a complex number. When we do complex numbers, when we add, subtract, multiply, and divide them, we're going to do that just like we would be doing like terms or multiplying binomials, dividing binomials. So the operations are going to work just like dealing with variables. So it really is pretty simple. With this, the plus tells us that we are going to add the like terms here with the like terms here. Really, the parentheses mean nothing here other than they're separating the complex numbers from each other. So we've got 6 plus 1 would be 7. Negative 4i plus 3i would be negative 1i. So the answer to that is just 7 minus I. For this one, similarly, we can add the terms that are alike. So 3 plus 2 is 5. 5i plus negative 4i is I. Here we have a subtraction. In subtraction, that subtraction sign has to distribute among both of those. If you don't distribute it, you will get the last term wrong every time. So this is 3 minus 5, which would be a negative 2. And negative 2i minus negative 4i, which is negative 2i plus 4i, would be a positive 2i. These are not alike. Same thing here. None of these were alike, so we can't go any further. That's as far as we can go. So when we add or subtract two complex numbers, we end up with a complex number. Here we have a whole number times a complex number. We're going to distribute that. Okay? Notice here the 2i, or the imaginary part, is in front of the real part. It really doesn't matter which side the imaginary part is on. It still works the same way. So 4 times 2i is 8i. 4 times negative 5 is negative 20. You could switch it around and say that that's negative 20 plus 8i. It really doesn't matter. I would just leave it like that. I think it's just as simple to leave it this way as it is to switch it. Next, we're going to learn how to FOIL these. If you have two complex numbers multiplied together, it just looks like two binomials multiplied together, so we're just going to FOIL. So if we do that, 6 times 5 is 30. That's the first term. 6 times negative 3i is negative 18i. 2i times 5 is positive 10i. 2i times negative 3i is negative 6i squared. And then we have to do a little simplification here. We've got 30. We're going to add these like terms. Negative 8i plus 10i is negative 8i. And then negative 6 times I squared is negative 1. So negative 6 times negative 1 is a positive 6. And then we add like terms. 30 plus 6 is 36. And that's minus 8i. So very similar to multiplying two binomials. Here, we have 2 plus 3i times 2 minus 3i. Hopefully you recognize those are conjugates. We can still have conjugates with complex numbers. There's nothing wrong with that. You need to recognize that if you have conjugates, the middle terms will always cancel out. So really it's only necessary to multiply the first and last terms if you recognize they're conjugates. I will do all four just so that you can see what I'm talking about. So we've got 2 times 2 is 4. 2 times negative 3i is negative 6i. 3i times 2 is positive 6i, and 3i times negative 3i is negative 9i squared. The negative 6i and the 6i do cancel out, which is what we thought would happen. We've got 4 minus 9 times I squared. I squared is negative 1, so negative 1 times negative 9 is a positive 9, and we've got 13. So if we have a complex number on the bottom of a fraction, if we multiply by its conjugate, we can get rid of all of the i's or all of the radicals by multiplying by the conjugate. That's something that's going to come up later. Here we have 3 minus 4i squared. Hopefully you remember that if we have a binomial squared, we write it down twice and we FOIL. So if I write it twice and FOIL, the first term gives me 9. The outside term gives me negative 12i, inside gives me negative 12i, and last gives me a plus 16i squared. I'm going to add my like terms. I've got 9 minus 24i plus 16i squared. I squared is negative 1. Negative 1 times 16 is a negative 16. So 9 minus 16 is negative 7 minus 24i. And again, you could switch it. You could say that's negative 24i minus 7. It really doesn't matter. Whichever way you like to write it is just fine.